Going to continue talking about graphs of trigonometric functions, and today we're going to be talking about damped oscillation. Damped oscillation looks like this: when the waves start getting really small and either continue getting really small or get small and then get big again. And it says because the values of sine bt and cosine bt oscillate between -1 and 1, something interesting happens when either of these functions is multiplied by another function. For example, if you consider the function y equals x squared plus 5 times cosine 6x, so you have a trig function times another function, in this case a parabola, and you can see that it's graphed over here in figure 4.65. The blue graph, which is the cosine function, that's your wave, is oscillating between the red graphs, the parabolas of x squared plus 5 and negative x squared plus 5. That squeezing effect right here. See where the waves get smaller? That is called damping. Okay, so it says the graph of y equals f of x times cosine bx, or f of x times sine. In other words, you have some function times cosine or some function times sine. Those always have to oscillate between the graphs of whatever this function is, the positive and the negative. When this reduces, it doesn't always, but when it reduces the amplitude of the wave, it's called damped oscillation. And the factor f of x, in other words, whatever they're multiplying the trig function by, is your damping factor. So your directions say, for each of the following functions, determine if the graph shows damped oscillation. If it does, identify the damping factor and tell where the damping occurs. Well, the only way to decide if damping is going to occur is to graph it. So if we type it in a graphing calculator and get the picture, you can see that here's my wave. It starts off big. It's getting smaller, which makes me think damping is going to happen. Getting smaller, smaller waves, and they continue getting smaller, and that's going to continue on forever. So yes, there is damping. See this little squeeze effect, how it's getting, the amplitudes are getting squeezed together, shorter and shorter. Okay, so yes, and then we have to identify the damping factor. The damping factor is whatever they're multiplying the trig function by, so in this case it'd be 2 to the negative x, and then it wants me to tell where the damping occurs. As x approaches infinity, the waves are getting smaller and smaller and smaller. So the damping occurs as x approaches infinity. And that is your answer. Okay? Alright, so same thing here. If I type it in a graphing calculator and get a picture of it, you can see that there is no squeezing effect on this. The waves are not ever getting smaller. They constantly are oscillating between +3 and -3. So no, damping does not occur, which means there is no damping factor and you can't tell where it damps. Okay, for C, we type that in and we get this picture, and you can see on the ends you've got these big waves and it's squeezed in the middle and then it starts getting big again. So here's where the damping occurs. But yes, damping does occur, which means my damping factor is whatever they're multiplying the trig by, which is y equals -2x. Alright, and then where does the damping occur? Well, this is occurring as x approaches 0. As x gets close to 0, the waves get smaller, and then they start getting bigger again. So the damping occurs as x approaches 0. Okay? Alright, so you try this one, hit pause, come back when you're ready. And hopefully you got damping factor is 3 to the negative x, and the damping occurs as x approaches infinity. If you didn't, let's look at the graph. I typed it in, make sure you're in radians, and I think my window went from -2 pi to 2 pi, counted by pi's, and my y went from -10 to 10. So you can see, yes, the waves start off big and then they get squeezed in right here, which as x approaches infinity, because it's not going to get big again. It's just going to keep getting smaller and smaller waves as you continue this way. So the damping occurs as x approaches infinity. Excuse me, hit pause, come back when you're ready. And hopefully you got the damping factor is negative 3x squared, and the damping occurs as x approaches 0. If you did not, let's look at the graph. And again, same window, I didn't change it. And you can see the waves are big, it's squeezing here in the middle, so yes, damping does occur. And that means that the damping factor is the function being multiplied by the trig function. And it's happening right here as x approaches 0. Okay, try this one. Hit pause, come back when you're ready. And hopefully you got no damping. If you didn't, let's look at the graph. And you can see that the waves don't ever get any shorter. They're continually oscillating between pi and negative pi. Alright, so a damped oscillation spring. It says Dr. Sanchez's physics class collected data for an airtable glider that oscillates between two springs. The class determined from the data that the equation y equals 0.22 e to the negative 0.065t times cosine 2.4t modeled the displacement y of the spring from its original position as a function of time. You ever like pull down a spring and then, no, probably not, but when you pull down a spring like a slinky, you know, for a while it's got its own momentum and it keeps going, and then it kind of finally peters out. Well, that's what's happening here. The spring goes boing, 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 but then the boings get shorter and shorter and shorter as time goes by. Anyway, they want us to, it does obviously dampen, okay, because the waves are getting shorter. So it says, what is the damping factor? Well, what are they multiplying the trig function by? So my damping factor is y equals 0.22 e to the negative 0.065t. Now B says approximately how long does it take for the spring to be damped so that y is between negative 0.1 and positive 0.1, meaning this function, when is it waving between negative 0.1 and positive 0.1? So I'm going to graph that, okay? I typed it in. My window, I went from negative 2 to 20 on x, counted by tens, and on the y, I went from negative 0.2 to positive 0.2, and I counted by 0.05s. Okay, why did I go to negative 0.2 and positive 0.2? Well, I'm trying to figure out when is it between negative 0.1 and positive 0.1, so I need to see a little bit above and below that. And what I graphed is, I typed in for y1, I typed negative 0.1. For y2, I typed in positive 0.1. And for y3, I typed in 0.22 e to the negative 0.065t cosine 2.4t. So that's what I typed in to get these pictures. So here's my positive 0.1 line, and here's my negative 0.1 line. And what I want to know is when is the wave in between those two horizontal lines. Well, you can see here, obviously, no, it's too big, too big, too big, too big. It's getting closer, a little bit above. Yeah, all right there, and right there. In this little area right here, that's when the wave is between negative 0.1 and 0.1. So what I want to do is figure out the coordinates of that point. So I'm going to calculate an intersection, and it's gonna ask you for left bound, right bound. All right, so I don't know why I changed my window, but I changed my window, and I calculated this intersection point. Okay, so I did my left bound over here, my right bound over here, and I got it is exactly negative 0.1 after 11.68 seconds. So about how long does it take? Approximately 11.7 seconds. Okay. Alright. It says graph both f and plus or minus its damping factor in the same viewing window. Describe the behavior of the function f for x is greater than 0. What is the end behavior of f? Alright. So what they want me to do when I go to type this in, for y1 you're going to type in positive 1.2 to the negative x. For y2 you're going to type in negative 1.2 to the negative x. And for y3 you're going to type in 1.2 to the negative x cosine 2x. And you would get this picture. Okay, so they want us to describe the end behavior of f. Well, for x is greater than 0. So from over here, the end behavior, as x approaches, you take the limit, as x approaches infinity, the function is getting closer and closer to 0. The waves are getting closer and closer to 0. Okay, so you try this one, hit pause, come back when you're ready. And hopefully you got the limit as x approaches infinity, the function goes to 0. If not, let's look at the graph. Okay, so the end behavior, this thing is going to continue to do this. So as x approaches infinity, the function values, the wave is getting closer and closer to 0. Okay, hit pause. Come back when you're ready. And hopefully you got 3. If not, let's look at the graph. Okay, for this one, as x approaches the limit, as x approaches negative infinity, my function is getting closer and closer to 0. Okay? So what is damped oscillation? It's when you multiply trig by another function and I never write this right, and the amplitude of the waves are squeezed. That's a good word, I like that one. Okay, how do you find the damping factor? Well, if it does show damped oscillation, the damping factor is the function multiplied by the trig function. And it says, where does damping occur? Well, it depends. It can occur in the middle. It can either do this and damp to the left. It can do this and damp to the right. Or it can do this and damp in the middle. Okay? And we are at homework, so we are done. Happy homeworking, and I will see you next time.